Imagine for a second being able to see in the dark.
Mm-hmm.
I mean, really see, not, fumbling with bulky night vision goggles, but just through your own eyes.
Maybe even like with your eyes shut?
Exactly. It sounds pretty futuristic, doesn't it? Like something straight out of sci-fi.
Uh-huh. It really does.
Well, get ready, because today we're taking a deep dive into research that's making that idea surprisingly real. We're looking at a brand new development in contact. Seriously.
Contact lenses.
Yep. Ones that could potentially grant wearers supervision, giving you the ability to see near-infrared light, stuff that's completely invisible to us normally.
Wow. Okay, that's definitely a fascinating area where optics and biology kind of crash together.
Absolutely. And this deep dive, it's based on sources you've provided. Specifically, there's this fantastic article from Live Science that just came out, May 22nd, 2025, digging into these supervision contacts.
Yeah.
So our mission today, let's unpack the core science, understand how these lenses actually work, see how they're being tested, and maybe explore what incredible things they might be used for down the line.
Sounds good. We're basically here to guide you through the important bits, the key insights from the research. Think of it as your shortcut to getting up to speed on this really cutting-edge tech.
Exactly. And as we go through this, remember, this is your deep dive. We're just your guides. If this sparks your curiosity, definitely hit like and subscribe so you don't miss our future explorations.
Yeah, and let us know in the comments. What other wild topics should we dive into next?
Definitely. Oh, and quick aside, speaking of online sources, the Life Science article itself mentions that they earn affiliate commissions through links on their site. Just a little context on how some online publishing works these days.
Right, standard practice for many sites. Okay, so the science. Let's get into it. The fundamental breakthrough here is creating a contact lens that lets you actually perceive near-infrared wavelengths of light. We're talking light in the 800 to 1600 nanometer range.
Which is way beyond the red light we can normally see, right?
Way beyond. So normally totally invisible.
So we're essentially adding like a whole new slice of the light spectrum to our vision. How do they even make that visible? It feels impossible.
Well, it all comes down to nanotechnology, specifically tiny particles embedded right inside the contact lens material itself.
Tiny particles.
And they're using flexible, non-toxic polymers. The same kind of stuff that's already used in regular soft contact lenses people wear every day.
Ah, okay. So the base lens is familiar territory. But the magic is in these little particles inside it. What exactly are they? What are they made of?
They have a pretty complex makeup. It's sodium gadolinium fluoride, and importantly, they're doped or sort of embedded with luminescent elements, things like ytterbium, erbium, and gold.
Gold. Wow. Quite a cocktail indeed.
Yeah.
So what do those specific ingredients do when infrared light hits them?
That's the core function. These nanoparticles, they absorb the near-infrared photons, the light particles that are invisible to us, right?
Right.
And then almost instantly, they emit that energy back out, but as visible light that falls within our normal sight range, roughly 380 to 750 nanometers.
So they're like microscopic translators, taking in invisible infrared light and spitting out light we can actually see. That's brilliant.
It really is quite clever.
And what makes this truly remarkable, as the source points out, is that unlike, say, traditional night vision, these don't need an external power source, do they?
Exactly. That's a huge point. Think about those old school night vision goggles, maybe from the World War II era or something.
Right, bulky things.
Yeah, they used electronic image intensifiers, needed batteries. They amplified existing low light or sometimes used IR illuminators, but they were complex. They didn't give you this kind of direct perception. These lenses work passively. They're powered just by the incoming light itself. And that's a total game changer for wearability, for being non-invasive.
That passive nature seems crucial. It's not amplifying, it's converting. Okay, so the science sounds pretty solid, but how do you even test if an animal or a person is actually seeing something that's supposed to be invisible?
That's a good question. How do you prove perception? Well, they started, as you often do in this kind of research, with mice.
Ah, yes, the brave little subjects. What did the mouse experiments involve? How'd they do it?
So they put the special contact lenses on one group of mice and then had a control group without them. Simple enough.
Okay.
Then they observed their behavior in a maze setup. This maze had some boxes that were dark and others that were illuminated just with infrared light.
Ah, so invisible light to normal mice.
Right. And what they found was that the mice with the lenses showed a really clear preference for avoiding the boxes lit by infrared.
They actively stayed away from the infrared light.
Yep. Whereas the mice, without the lenses, they showed no preference at all, didn't care.
Interesting. So why is that avoidance behavior significant?
Well, it mirrors how mice, who are naturally kind of wary of bright conditions because of predators, right?
Mm,
It mirrors how they'd react to normal visible light. So it strongly suggested they were perceiving the infrared as a form of brightness, something to avoid.
that's a very clever way to test it behaviorally.
Mm.
Were there other ways they confirmed the mice were, seeing it, not just
Yeah.
reacting weirdly?
Yeah, they backed it up with neuroscience too. They did brain scans.
Oh, cool.
The scans of the lens-wearing mice showed their visual processing centers were actively firing when they were exposed to the infrared light.
So the vision part of the brain lit up.
Exactly. Plus, another physical sign, their pupils constricted, got smaller, which is another involuntary physical response our eyes have when perceiving light.
Okay, that's pretty solid evidence in mice, though. Behavior, brain activity, pupil response. What about moving to human testing? How did that go?
They did. The team tested the lenses on people too, and the results there were also pretty compelling.
Okay, what could the people do?
Participants wearing the lenses were able to perceive flickering infrared light, and they could even tell which direction it was coming from.
Flickering light. Why
Yes.
flickering? Is that important?
Yeah, using a flickering light or some kind of changing signal is a pretty standard method in vision science. It helps reliably probe the brain's visual pathways. It often gets a stronger, more definite response than just a steady, constant light.
Gotcha.
But here's where it gets really interesting and, frankly, kind of surprising.
Okay.
The participants' ability to perceive this infrared light, it was actually better when they closed their eyes.
Wait, hang on. You're saying they could see this invisible light better with their eyes closed than open? That seems completely backwards. How is that even possible?
Yeah, it feels counterintuitive, right? But it boils down to how different wavelengths of light interact with, well, tissue, like your eyelid. As one of the lead researchers, Tian Xu, explained it, when the subject closes their eyes, they're even better able to receive this flickering information. Basically, near-infrared light is actually very good at penetrating soft tissues. Your eyelid doesn't block it much.
Ah, okay. But visible light is blocked by your eyelid mostly.
Exactly. So when your eyes are open, you've got all the normal visible light hitting your retina too, right? That potentially creates visual noise or interference for this new infrared signal the lens is creating.
Right, makes sense.
But when you close your eyes, the eyelid acts like a filter. It blocks out most of that competing visible light.
Allowing the near-infrared light, which passes right through the eyelid, gets converted by the lens to provide a much cleaner signal to the eye.
You got it. The eyelid, strangely enough, helps clarify the infrared perception. It's a really remarkable finding. And like Dr. Su said, without the contact lenses, the subject cannot see anything, but when they put them on, they can clearly see the flickering of the infrared light.
Wow, a dramatic demonstration then. Seeing the invisible and seeing it better with eyes shut. That detail alone is just fascinating.
It really is.
Okay, so enabling humans to see infrared light is obviously cool on its own, opens up these potential supervision applications. But what are the more immediate practical uses they're thinking about for this technology right now?
Well, the immediate applications mentioned in the source really revolve around that ability to perceive the specific flickering infrared signal we talked about.
Right.
That capability could be really valuable in areas like security. You could have hidden infrared markers for, say, verification or secret signaling.
Like invisible ink you need special eyes to see.
Kind of, yeah. Think about rescue operations, maybe guiding people in low visibility. Or anti-counterfeiting measures on products. Even secure communications where only someone with these lenses could perceive the message.
Okay, using infrared as a kind of hidden channel. That makes a lot of sense for specific tasks. Is that the main potential, or is there more?
Oh, far from it. The researchers also explored another incredibly exciting potential application, using this tech to help people with color blindness.
Color blindness, really? How does seeing infrared help someone distinguish between, say, red and green, which are visible colors? That seems like a different problem.
It does, but this is where the versatility of those nanoparticles comes back in. The scientists figured out how to modify them to do more than just convert infrared to any visible light.
Okay.
They could actually map specific parts of the near-infrared spectrum to emit light as specific visible colors, blue, green, and red.
Whoa. So instead of just one uniform conversion, like turning all IR into, say, green light, they can create a kind of translated palette.
Precisely. They can control the output color. And the idea here, as Tianziu explained it, is that by converting red visible light into something like green visible light, this technology could make the invisible visible for colorblind people.
Okay, hold on. converting red visible light into green visible light. How does that work? I thought it converted infrared.
Ah, good catch. It seems like the idea might be a bit more nuanced, perhaps involving converting troublesome visible light into a different visible light via an intermediate infrared step, or maybe using tailored nanoparticles that respond differently to different visible wavelengths. The core concept, though, is remapping colors.
So taking a color someone struggles to see, like certain shades of red.
Exactly. And using the lens technology to effectively shift that input so it's perceived as a different color, one they can distinguish clearly. Maybe shifting problematic reds towards the green part of the spectrum for someone with red-green confusion.
Wow, okay, that's a potential application that moves way beyond just extending our senses into a new spectrum. It's actually helping correct or augment perception within the standard visible spectrum.
It really is. It demonstrates the power of this nanoparticle approach. It's like a flexible light converter, potentially tunable for different needs.
This all sounds incredibly promising. I mean, seeing infrared,
Yeah.
potentially tackling color blindness, but obviously, we're not picking these up at the opticians tomorrow. What are the big hurdles? What needs to happen next?
Yeah, you're absolutely right. This is still very much in the research and development phase. There's significant work needed before they're ready for widespread use.
What are the main limitations right now? What's holding it back?
Well, a big one is sensitivity. At the moment, the lenses really only work well when they're detecting light from relatively bright sources. Think strong LED signals.
Well,
Their sensitivity needs to be boosted, dramatically, to pick up lower intensities of light. Things like the faint infrared radiation that objects naturally emit just from their temperature or, body heat.
so you couldn't use them yet, like military night vision, seeing a person hiding in total darkness just from their heat signature.
Not with this current version, no.
No.
Not sensitive enough. Another challenge is resolution.
Resolution, meaning how clearly you can see details.
Exactly. Because the contact lens sits directly on the eye, right on the cornea, its closeness can actually limit the ability to resolve fine details within the infrared image it's creating on your retina.
Is that sort of like how holding something too close to your eye makes it blurry? Or is it a different optical thing?
It's related to the optics, yeah. It's about the fundamental limitations of forming a sharp, detailed image at that very close distance using this specific conversion method.
Okay, so sensitivity and resolution are the main technical challenges. Are they working on fixes?
They are. To tackle that higher resolution problem specifically, the researchers are actually developing a separate system. It's a wearable glass system. Think more like eyeglasses than contacts.
Ah, interesting. A different form factor.
Yeah, and they believe this glasses-based approach will allow for much higher resolutions when you're actually trying to view infrared-emitting objects in detail, not just detect a signal.
So maybe contact lenses for sensing signals or basic detection, and then a glasses system for more detailed infrared observation. That sounds like a logical path.
Exactly. It shows they're thinking strategically about different potential use cases and how the actual form factor lens versus glasses impacts what you can do with it.
Okay, so let's recap this deep dive. We've looked at how scientists are using some really cutting-edge nanoparticle tech, embedding it in contact lenses.
Right, to potentially grant us a form of supervision, letting us see in the near-infrared spectrum.
Yeah, and we saw how they proved it works, from those mice avoiding the infrared-lit boxes.
To that really surprising finding that humans can actually perceive it better with their eyes closed.
Totally wild.
Oh.
And we explored the potential applications, beyond just seeing IR. Things like hidden security signals, maybe rescue tech.
And that truly exciting possibility of someday helping people with certain types of color blindness.
While also acknowledging, the hurdles still there, the need for much better sensitivity and higher resolution.
Definitely. This research, it really highlights how fields like material science and neuroscience are coming together. They're pushing the very boundaries of what human perception might be capable of, all stemming from the kind of sources you bring us to dive into.
Absolutely. And what's truly fascinating here, I think, is the potential for extending our senses in such a non-invasive wearable way, right in your eye. If we can use technology like this to perceive near-infrared light, what other parts of the electromagnetic spectrum might we eventually be able to perceive? Maybe ultraviolet, maybe even radio waves someday with future wearable tech.
It really makes you wonder, doesn't it?
It does. It raises this really important question about how we even define the natural limits of human vision and perception itself. Where does biology end and technology begin?
It definitely opens up some incredible possibilities to think about long term.
Indeed. Well, that was another deep dive, unpacking some pretty complex info from your sources and hopefully giving you some aha moments along the way.
I hope you found it interesting.
Keep that curiosity flowing. Don't forget to like and subscribe if you enjoyed this deep dive. And please let us know in the comments what topic we should explore in our next one.
Yeah, we'd love to hear your ideas.
Stay tuned for more.